Quantum mechanics is more fundamental than classical mechanics, and this is because quantum mechanics explains why classical mechanics behaves the way it does. Richard Feynman taught us that the probability amplitude for a particle to propagate from some fixed initial position to a fixed final position can be calculated using something known as the path integral formulation of quantum mechanics. In a nutshell, this formalism tells us that in order to calculate such a probability amplitude, we need to add up all of the contributions from every possible path that propagates forward in time that the particle could take between these two positions. This leads to the following formula, in which our sum results in an integral over all paths connecting these two endpoints, where each path contribution is weighted by a phase factor. The explicit value of this phase for a particular path is given by e to the I over h power times s of q, where s of q is the corresponding classical action of the particle evaluated along the particular trajectory of interest. You can think of this phase as assigning a vector of length 1 centered at the origin that points in some direction around the unit circle to each path. So how does classical mechanics pop out of quantum mechanics? Well, the action has units of energy multiplied by time, but on the quantum scale, the energies that we're dealing with are very, very small in comparison to those that appear in the macroscopic scale. Since h-bar also has units of energy multiplied by time, it makes sense to compare these two quantities and consider what happens to our path integral in the limit that s is much bigger than h-bar, as is the case with objects that behave classically. In this limit, the changes in action between the set of paths that are integrated over are much larger than the value of h-bar, and hence the path integral begins to oscillate wildly. The only paths, therefore, that contribute to the path integral in this limit are the ones such that the variation in the action evaluated on this set of nearby paths vanishes to first order, where the rapid oscillation effect is damped. Contributions from such an equivalence class of paths constructively interfere, and thus in the classical limit, the trajectory that dominates the path integral is the one whose variation in action vanishes to first order. And this is precisely the statement of the principle of stationary action, from which classical paths emerge as the solution to the Euler-Lagrange equations, which is an equivalent formulation of Newton's laws in classical mechanics. So there you have it, the laws of the classical world around us, explained by Feynman's beautiful interpretation of quantum mechanics using his path integral.